So, so last time we looked at these just give me a second. Okay. So last time we talked about the idea of Nadaria-Watson estimation of the regression function using these kernels, translation invariant kernels, that they have, each one has a bandwidth h, and we translate and rescale one particular kernel by bandwidth h. And so this was what they look like. And we saw that these guys would, yes.
Why do we use kernels to reduce dimension, or the kernels used to increase dimensions?
We are not here using them to increase or decrease dimension. We're using them to form similarity. So what you want to do is to find a similarity measure between your training examples and your new test example. So this is a way of measuring similarity.
Wouldn't like PCA do the same or similar thing?
So kernels are used in many different places, but kernel, if you want to, like, one thing to know about kernels is that they are sort of measures of similarity. So that's what they're used. Like bivariate functions, usually they mean, like, if it's larger, it means the two samples are similar. So if you have k of x and x prime, if this is very large, then you're saying that they're similar. If this is very small, they're not similar. So usually the kernels that we construct, they have that meaning. So for example, the Gaussian kernel, you can see at 0, it's the highest, maximized. And as you go down, it gets smaller. So when you look at the samples x and x prime, when you form the difference, if the difference is very small, you're here, so it gets very large. If they're very far apart, you're in the tails, so it gets very small. So it's like measures how similar they are. Similarly, that box kernel, if the distance is like for a given issue, you do change the bandwidth of this. So if they're in the same like little interval, then the kernel is like the value is high, otherwise it's 0. So they're very dissimilar. So it's a very harsh way of deciding similarity. They're either this close, in which case they're similar, highly similar, otherwise they're highly dissimilar. So that's the box one. It's a way of measuring similarity, right? And the reason why, yes.
Go ahead.
Yes, and the reason why we did this was because we tried to extend the idea of remember the idea that we had here. This was a natural estimator. And if you think about this indicator, it's a very natural way of measuring similarity. You say x is similar to xi if they're exactly the same. We wanted to relax this assumption. Yes.
In the different type of kernels, what does the variable u stand for?
Can you say that again?
What does the variable u represent for the different types of kernels?
Where is u here? Oh, is it?
In the
You mean the h?
yeah.
Oh, yeah, u here. Okay, you're talking about this.
Yeah.
Oh, that's a dummy variable. So what I'm trying to say is that you can come up with a univariate or like function of one variable. It's like the Gaussian. So in the univariate case, it would be like e to negative u squared over 2. And then you do translation invariant. So I can apply it, let's say, to x minus x prime divided by h. That would give me e to the negative x minus x prime squared divided by 2h squared. So that's just a dummy variable that I'm using here. Doesn't like just defines the function, right? So the only thing that we need here is like usually the way that these work is that they have to be large near 0 and go down as you go away. Okay, any other questions? And you saw that this is a fairly simple, that gives you a very simple way of constructing fairly complicated classifier. So this is, so we didn't know anything about the data, we just formed this sort of weighted average using like a weighted average, as we pointed out. So it's a weighted average of yi's. You're training y's with the weights being determined by these kernels, and the kernels are, in the case of Nadari Watson, are like these translation invariant kernel, but there's a lot of choices for them. We'll see another example. We actually talked about k-nearest neighbor is an example of this with a particular k similarity. Today we're going to talk about partitioning estimators as well. But then it gives you a very simple way of constructing these regression functions. So we're going to add one more name here. So this is a non-parametric, they call it a non-parametric. So this is going to be a non-parametric estimator. We'll see what, in contrast to parametric estimators, for example, logistic regression is parametric. We'll see. This gives you a non-parametric estimator. Basically, it doesn't assume any shape for the regression function. So you're not a priori assuming that this regression function goes from 0 to 1. We didn't assume that. It just came out like that. Okay, it could have been, the data could have been like this, 0 here, 1 here, and 0. This would fit something like this. So it doesn't assume a particular shape for the regression function. So everything is fine except that this bandwidth, like you can see there's sensitivity to bandwidth, and we talked about this bias variance trade-off. If the edge bandwidth is small, then you have the ripples, which are an indirect manifestation of the variance. The variance of the estimator is high. And if we have that edge is large, then these kernels are going to be like more diffuse. So you can see the blue one here is a kernel with a large bandwidth, very diffuse. This one is a kernel with small bandwidth. It's very narrowly concentrated. So these narrower ones would give you, like, because you add them up and the support, where they put mass is like sort of disjoint, you get these bumpy functions when they're very diffuse for large bandwidths. They're basically all gonna like smash together and sort of average things out, so you get these very smooth curves. So, and then the black one is sort of something in the middle. And we talked about decision boundary. The decision boundary here is like, if you care about accuracy, this gives you an estimate of eta hat, and then you threshold this at 1/2. It gives you a decision rule or the classifier. And we talked about that the fact that the decision boundary here is not that sensitive, or like the classifier is not going to change much. Although the regression function is changing a lot, the classification rule is not going to change as much. And so this tells you that classification is a simpler task, like an easier task than regression. Okay. And then we talked about how to choose H, if you remember. So the only training that here you have to do is pick H. Once you have the training data, once you have that, then you have the entire classifier. You can apply it to any data you want. And so how do we choose H? Anyone remembers? If you want to apply this in practice, you have to pick one H, right? How do we do that? Yes.
The one that would minimize the test there.
Yes, good. So you split your data and then you train on one part. Basically, there's no training here. So you form the statistic, like the eta hat, and then you evaluate it on the test data. So the training, basically the x's go, so the x and y go into this. So 0 training time, but the x and y from the training goes into constructing this, and then you apply it to the x's from your test set. And then you get an approximation of, your test error. So for each one of these, so there is an edge here involved for each one of these eta hats. So you get the decision rule based on edge, and you get this test error of f hat edge, and you plot it as a function of edge. And you actually don't need to plot it, but it's good to plot it, and you get something like that. And you see, for example, there is a dip here. So this would be a sort of optimal choice of the bandwidth. Too large or too small, increases your classification error, but this is like a good choice. And then you can see because it's sort of flat, it varies very slowly. It tells you that it's not as sensitive to bandwidth as the regression function suggests. Okay. Sounds good. That was last lecture. Questions? So what I want to do is also talk about the partitioning estimator. So and then what I want to do is sort of try to characterize this bias variance trade-off a little bit more mathematically, more theoretically, so that you get a better sense of it. And we're going to do it in the context of regression, not classification. And so we introduce the regression problem as well. So far we have been looking at classification like exclusively, but you can see this regression function coming up. And we're going to talk about that and you can see that we already have an estimator of the regression function as well. So we can do regression already for free. But before that, so partitioning estimators. So these are like, again, very simple application of that general framework. So we had eta hat x summation. So it's like a similarity measure here, yi divided by summation kxi and x, I from 1 to n. So what I can do is, in the case where the distribution of x is supported on a bounded set, for example, in the univariate case, what it means that I can find like an interval such that whenever I sample from the distribution, like I'm always in this interval. So the distribution had puts all the mass here. Let's say for simplicity, this is 0 to 1. We can always rescale all our like covariance or like these x's to be in 0 to 1 for simplicity. So the partitioning estimator just like partitions this into a sequence of like a collection of sets, disjoint sets. So the simplest thing to do is like take a length h and then partition it into like equal sized intervals of length h, let's say. So this is the length would be h, and they're going to be roughly like 1 over h of these intervals. Okay, and then when I look at my x's, the x's are going to be like some of these intervals will have more x's, some of them would have less. So these are the training x's. So training. So they're going to like fall into these bins. So for example, you can like count in each bin how many you get, and that gives you a histogram. That's an estimate of the distribution. But I can also use this to construct a kernel here. So the kernel would be, I'm going to say this is equal to the indicator that xi is in a of x. So a of x here is going to be, so if you go pick an x here, given x, a of x is just this interval in which the x lies. Okay, so for any x, so the cell of the partition, so this is, let's say x, this is my test point. So this would be a of x, the cell of the partition, onto which the x falls. Okay, so for example, if I have another one, like this x, that would be like x prime, this would be a of x prime. Okay, I'm going to look at x, and any xi that's in the same cell will have like similarity 1, otherwise 0. Okay, that's if you plug that in there, that would give you the partitioning estimator. So that's the partitioning estimator. So what it means is like I'm going to sum basically, when you do this, you're going to average, this is going to be your estimator. right? At a given X, that's my test point. There's going to be a regression estimator. What it's doing is it goes and look at all the training examples that are in the same cell. So in this case, there's nothing, so it's undefined. But if X turns out to be in this cell, I have one, let's say maybe I have two. For those two, this is going to be active. So I'm going to just average the yi's for the ones that are in the cell. So it's a very simple procedure. Mathematically, it looks a little bit strange, but intuitively it's simple. So you go and see how many of your data points are in the same cell of the partition, and you average the yi's over those x's. That would be your regression function estimate. This is like the estimate of the probability of y equal y, one given x. So this gives you an estimate of the probability. And then you can threshold it, you can get a decision. Okay, yes.
So I realize that with looking at the partition,
Yes.
it's a measure of similarity. Like what if, like, you know, you have an xi, which is super close to x, but it might just be the other position.
That's good. So this is, yeah, so very nice example. So once you have the partition, the thing is, these partition cells are determining the similarity, not the distance. So you could be like, X maybe is here, and then you have an XI, which is very close here, but they're going to be indifferent. So the issue with this is that it's going to like, it says that they're dissimilar, right? It's the nature of it. If you care about the distance, so these are more natural. So for example, Gaussian one, these like the translation invariant, that's where the sort of translation invariant comes in. It doesn't care about where things are as long as the distance is small. So if you prefer that not happening, this is your estimate, right? So you'd use a Gaussian kernel, it doesn't care. So there's limitation to this. But there is some sort of there is a similarity of this partitioning estimator with the box kernel. So if you think of the box kernel says, I'm going to pick each xi, I'm going to put an interval of length h around it. And if it captures x, then it's going to be similar to it. Otherwise, it's not. This is very similar, but it's slightly different. It's even simpler. So you lay out your partition and then see how many like points or which points are within the same cell as yours. Those are similar, other ones are not. So it's not distance based. It has some advantages in spaces, let's say, in which there is no distance. So you can partition things, but there is no measure of distance, right? You can always find partitions. It may not be like that. So this is based on distance, but you can partition based on other criteria. Okay. A lot of estimators are actually, so for example, decision trees in general for continuous variables, they look like these partitioning estimators, but the partitions are defined by the data itself. So you can define data derivative partitions. And in fact, k-nearest neighbor is very similar to this, but with a data derivative partition. I might talk about that. But yeah, so this is a very dumb way of partitioning. Ahead of the time partition equally, like into equally spaced one. But if you allow the partitions to be more like maybe data derivative or like do it not based on distance, based on some other criteria, maybe that might give you something which is more interesting. But the thing is that this is actually going to work fairly well. And depending on like the type of thing, it's not the optimal thing to do, but we'll see. We can. The reason why I'm introducing is because this is the easiest to analyze among all of them. Okay, this is the easiest, but it captures the idea. So you can see this H behaves like the bandwidth. It's very similar to the bandwidth of this box kernel that we looked at. Right. So this box kernel, if you think about it, it just doing something similar, but the intervals are sort of centered around the trainings data points. They're not fixed ahead of time. So I'm fixing things ahead of time for the partitioning. So for this one, you're basically putting these intervals around every one of them, and then every one training. But it's very similar to this. So this H behaves like a bandwidth. So you'd expect if I reduce this H, the variance of the estimator would go up because it would capture fewer data points in each one of them. So your estimate of the regression function is based on a fewer number of data points. If I enlarge H, then each interval will capture a lot of data points, so the variance would go down because I'm now averaging over more points. but then I'm gonna mixing around like all the x's. So if the interval is large, the regression function could vary a lot on that interval. I'm just treating them as all one. So I'm like averaging over those. So you incur a large bias. So that's what I want to like show you. Right. So it would be like the regression function is varying like that. If I take a very large interval, maybe it's like varying like this, or I'm going to average all these values together. So eta of x here and here, it doesn't matter. All of these xi's, the eta xi, the true ones, I'm going to average over. But if it's very small, I mean, you'd imagine that maybe everything that's in this interval has the same similar eta. So it's averaging over those, doesn't incur a lot of bias, but fewer points will be in that interval. So you would have a lot more variance. So that's what I'm gonna try to get. Okay, so increasing these partition lengths would increase the bias because you're treating all these x's, basically everything here as the same, having the same. If the regression function was flat here, it would be perfect. But what it's gonna do is like approximate the regression function by a flat thing here and a flat thing. So in each interval, basically the regression function. So what if you go and evaluate this function, you'd see that it would be like exactly constant over each one of these partitions. So it would be like either 1 here, like something between 0 or 1. So if it's 0 to 1, so it would behave like this. So it would be piecewise constant. And piecewise constant functions are not necessarily useful. Not necessarily useful, but if the regression function was like that, you would approximate it like this. So you get some approximation, which is piecewise constant. If you decrease the intervals, you'd get a closer approximation, right? These steps would be closer. If you increase the length, it would be like the entire thing here is just going to be constant, and then the entire thing would be here constant, something like that. So you get this is having a lot of bias. The middle one is okay. The red one has a small bias, but the variance would be higher because in each one, this level is going to vary a lot because it's an average of a smaller number of pieces. That's what I'm gonna try to show. Okay. So we have partition estimators. These are piecewise constant approximations to the regression function. It turns out that the k-nearest neighbor is an example of this, but the partitions are not these regular things. They're dependent on data. So it's piecewise linear. I might show it later, but on like partitions that are cells of the partitions are strange, defined by the data. Decision trees are like that as well. They're piecewise constant. They're like these partitioning estimators, but again, the cells of the partitions are determined by the data. Questions? So like the partitioning estimator now. Nearest neighbor, we talked about that. I'm going to come back later. So any questions about the partitioning estimator? So the plan is to try to analyze this and see the bias variance trade-off as a function of edge more clearly. I just want to, if you see one example, it gives you a lot of intuition about what is going on. So in order to do that, questions? I'm going to introduce a regression problem you already know. So how many people know regression? Okay, so what is regression? What is the regression problem? So what is classification? Binary classification? Yes.
So classification is basically the Y output is trying to predict a bunch of like discrete values.
Yes. Yes, exactly. So the only difference really is that the response variable target is in regression, it's a real value object, but the continuous variable classification is a discrete value. In binary classification, there's two values. Usually they're called 0 or 1, positive, negative. Regression is like, I'm going to still try to predict based on the covariant X, the response whether the Y is like variable. What we're going to look at here again is from a decision theoretic perspective. So what I'm going to have is I'm going to have a rule, like we used to call it this classifier, you can call this, I don't know, regression estimator. It's going to be like a function of X. This is, we're going to call it Y hat. And that would be my estimate for every Y. So we have a pair of XY, right, from an unknown distribution. Now Y is real. That's the setting. And then given X, you want to predict Y, so I'm gonna come up with a function F that tries to predict this. If this is gonna be real value, so if it's gonna be from my sample space to R. And what I'm gonna do now is I'm not gonna use the 0, 1 loss because it makes sense for classification, but this is a continuous value, so I'm gonna use like a quadratic loss, for example. So I'm gonna measure the distance squared, that would be my loss, it's a quadratic loss or a squared error loss. And so the risk, again, is the same, it has the same kind of expression, expected loss. And in this case, if you evaluate it, it would be expected a squared error or mean squared error. So it's the MSE, it's called the MSE. So we're going to work with the risk, but the risk here is going to come from the quadratic loss and it's called the MSE. Okay, so within the same framework, I just changed the loss because my target is not binary. So 0, 1 doesn't make much sense. Okay. 0, 1 loss, still I can use it, but most often I'm not gonna. So the 0, 1 loss is very strict here because it says if Y hat is not equal to Y, then I'm gonna pay it like a maximum price. Otherwise, it's 0. And most likely in regression, you can't pin down the exact thing. So you don't want to be penalized that severe. This is more relaxed. If you're close, you're gonna pay like a smaller loss. If this is large, you're like not doing good, you pay a bigger price. It's a continuous loss varying as a function of Y hat. Okay, so that's the setting. Okay. So then we can go over all the things that we did. So for example, you can ask what is the, if I know the actual distribution, the oracle problem that I mentioned, if you remember, what is the optimal thing to do? What is the optimal decision? Anyone remembers from the homework problems? So you already know what the prescription for the optimal decision rule is. So if you have read through the notes that I posted, the argument is very general. If you have a loss function, if you have a risk, there is a prescription to come up with the optimal rule, assuming that you know the actual distribution. So what is the optimal rule? How do you like find it? Yes. So minimize the MSE, that's what you want. The optimal was the one that minimizes the MSE, but then you like write a prescription for like, that's what we want. We want a rule, again, sometimes called Bayes rule, if you want to call it optimal rule. Optimal Bayes rule is the one that has the smallest MSE. So R of that F star is going to be less than R of F for any other estimating. So there was a problem that gave you that this is like arc min of something. You remember? Yes.
Are we assuming Y is either always like
No, we're assuming it to be in R.
or
But that problem also like was general. So if it was classification, what would you do?
probability of Y equal 0?
I'm gonna write it if you wanted to write an expectation for
Oh.
expected loss of Y, and then you put a decision here, given X, equal X, and then you minimize over D. It used to be D in 0, 1. Now I'm gonna do D in R because my decision can vary in R. So that gives you the general form. So you're gonna always minimize the posterior risk. So this is like a risk, but conditional on X. Once I condition on X, because this is, remember, this is F of X. Once I condition on X, this is like deterministic. So I can plug in a D here. And if for every X I can minimize this, then we can argue that the overall thing is going to be minimized. So that's the argument. We go through the notes. Follow the basic thing that we did in the case where Y was binary and the covariate was binary, and then we extended the case where Y was binary, covariate was continuous. This is an extension to Y in any space and X is in any space. Still works, and the loss is general. But still, the rule is the same. So you look at the loss, take the expectation conditional on X equal to X. So this is only dependent on the conditional distribution of X given Y. And this is going to be a function of d, I'm going to minimize it over d. Okay, so in this problem, for example, for this loss, for quadratic loss, this turns out to be, you can just write it. It's not going to be a probability anymore, so it would be y minus d squared, conditional on x is equal to x. And then I want to minimize over d. Okay. I'm just replacing the L with the definition. So how do we do that?
Instead of some summation and secondary.
There's a simpler way of doing it without taking the, you can, yes, you can try to. Generally, the expectation here would be an integral. You can do summations if you want. But because it's quadratic, I can expand the quadratic. Things would be simplified. In this case, you don't actually need to calculate that much integral. Like there's no exam. If you want, you can try to write it as an integral. Right? One way of doing it is to write this as, say, this would be like y minus d squared times p y given x of y given x integral dy, and then try to minimize over d. That's like a way of writing an expectation. But so alternative would be, in this case, expand the quadratic. So alternative approach, expand the quadratic. So can anyone tell me how to expand the quadratic? Everyone knows probably like how to expand y minus d squared. Y squared. Yes. But yeah, conditional on x. Now, what can I simplify here? So conditional expectation is like expectation, and expectation is linear. People know what that means. Expectation is linear. Separate, yeah, I can say expectation of y squared given x equal x. You can just imagine this gone. This is going to be everywhere. So, and then what? Minus. I would say, okay, so I can say like plus expectation of the other term minus 2yd given x is equal to x plus the expectation of d squared. This is linearity. So what is this term? The simplest one. It's going to be d squared because d squared is constant here. How about this? Negative 2d comes out, you get expectation of y given x. So this thing we have called eta x. So this is the actual regression function, if you remember. We use the same notation. How about this? This doesn't simplify, but just we leave it there. Okay, so you get expectation of y squared conditional on x is equal to x minus 2d eta of x plus d squared. Okay, so that's the function. And I want to minimize this over d, if you remember, right? So how do you minimize this function over d? What is the minimum? Take the derivative, yes. Like the simple way, usually easy way, if you can, take the derivative. Respect to d, this is a quadratic function. You should know that it has a minimum because the sign here is positive, so it's like convex. If you take the derivative, set it equal to 0, you're not guaranteed to get a minimum. You're going to get a stationary point. So you know that if it has a minimum, it's going to be among these stationary points. But in this case, there's going to be one stationary point that will be at a minimum. So take the derivative. Someone, how do you take the derivative? Differentiate with respect to d. What would I get? What happens to the first term? Gone. Second term? 2 eta of x. And then let's do d equal to 0. What do I get? Yeah, so d is equal to eta of x. So the argmin is the value of d that minimizes. We can verify that this actually minimizes that. This is like a quadratic. It's like this. So the minimum, there's a minimum in that. So the solution to this turns out to be eta of x. So f star is actually eta of x, and eta of x is just the conditional expectation, right? So that was this. So we saw, like we showed that conditional expectation of y given x is actually the optimal rule for the quadratic loss or the MSE, right? So this unifies classification and regression from a decision theoretic perspective. This is the decision theoretic perspective. You want a decision rule, you want a classifier, you want a regression. These are called decision rules. And this, you put a loss and then you have a risk and you try to minimize the risk always. And the solution of that is your optimal rule. That's what you're after. So in the classification case with the 0, 1 loss, the optimal rule was find the regression function and threshold it at 1/2. In the classification with the MSE rule, it's just this entire function itself. So there's this very simple link between classification with 0, 1 loss and regression with the MSE. It's just this regression function is playing the main role. Okay, so now we have regression. Is this clear to people? It just this one go through the exercises. There's an exercise to talk about. I haven't assigned it, but this part, this works for any decision rule, for any decision problem, for any loss, any type of y space, and so on. And it follows from the discussions that we did. In the case of classification, this was 0, 1, so the expectation was the probability. No, it's just expectation itself. Okay, sounds good. Yes.
So I realized that if x is the expectation.
Yes.
Y for the value of x and not probability.
Yes.
Why is that compared to the classification?
The classification was the same. So what you would do is like the expectation of this, but this loss was, so in the classification, the loss was y hat minus y, the expectation, like the 1, right? So the rule would be f star x argmin d in 0 to 1, expectation of L, y, and d given x is equal to x. If you plug this in, L, y, and y hat, so plug this in here. So the expectation of an indicator would be the probability, remember? So that would be equivalent to this, right? Sounds good. And then you can go through everything. And then we saw that if you do this, it would simplify and solve your homework problems to finding eta and translating, like thresholding it with 1/2. So the same is like the decision rule is the same always. The formula is the same, just the loss function changes and the space of y changes. You get different answers. But fortunately for us, we got x here for which we actually know an estimator. So this estimator, although I did it for binary y, and you can see in this case turns out to be like, because y is binary 1 or 0, it turns out to be these smooth things that go from 0 to 1. But this regression estimator, if you think about it, this actually works for general y. So this is a general estimator for any general y, like as long as y is real value. You can think of where this came from. This is actually a good estimate of the regression function. This is a regression function in the case of binary, but this actually works for a discrete x and y being real value. So if y was real value, but x was discrete, this is going to be an estimate of eta. Think about this yourself. This would be an estimate of conditional expectation. And the same thing happens for this because it's an extension. So I let you think about why, but doesn't matter if it's 0, 1 or real value. This is still a good estimator. So this is actually Larry Watson estimator is like designed for doing regression non-parametrically for y that's real values. Okay, so everything that we talked about works for a general y. Okay. It's just that when you want to do classification, this, because yi's are 0 to 1, it turns out that this eta hat, like, it remains in 0 to 1. That's the expectation of a random variable that's taking value 0 to 1. It's going to be like smooth between 0 and 1. If y took like real values, then this would be just, so y could be like everywhere here instead of 0 to 1, and then the regression function, this function, if you calculate it, would like do something like that. You could go like to infinity or whatever. So you can do this as an exercise. I can assign it like homework problem. You should assign, maybe remind myself to assign a homework problem to do that. But everything that we did for the regression function works. Okay, so we now have an estimate of the regression function in the form of Nadaria-Watson. The reason why I introduced this is because now I can measure the performance. So think of this as if this was, we can view this as a like regression problem as well. If this was a regression problem, I would care about this exact function everywhere, because that was my optimal rule, and I want to compare this at every point to the true regression function and take an average over x. I care about the MSE, so these ripples matter. So for regression, because our loss is sensitive to everything, like every value of x, so then I can better demonstrate to you the effective edge. So that's why we're looking at regression. Besides the fact that like statisticians also like regression. If you're an ML person, you rarely work with regression, mostly like classification, multi-class classification. But statisticians start with regression and usually don't go talk about like classification. Very barely talk about classification. So for that reason, we started with classification because it's also like not as obvious to you probably because of your background in statistics. But everything that we did so far, at least the estimators work. And I just want to show that now, for example, you have really, can you see that? So there is a bias. So now you see that this is the target that you're after. This is our optimal rule. I want this at every x. And then there is an expectation of this, which is it's going to be close to this sometimes at some points, sometimes not. So now I'm going to study, actually, I want to study the MSE. I want to study the MSE for our estimator, this quantity. Okay, is the plan clear? Sounds good. So we look at regression, change the loss function, MSE, the optimal rule is the conditional expectation of y given x, which is what we call regression function. We already have an estimator or like a class of estimators or regression function. Everything that I talked about, Nadaria-Watson, kernel estimates, the partitioning estimator, the KNN, all of it works for this as well, because all of, if you could just go imagine that yi is like real valued, all of those work, and they're good estimators of eta x. Now we're going to compare eta hat to eta x. So what I want is sort of, if you have an estimator, basically you want R of eta hat. Okay, so eta hat is that Nadaria-Watson or like kernel estimate or the partitioning estimate. Like in practice, how can I measure the risk in this case? How do I measure the risk if I want to like see whether Nadaria-Watson is doing good? You can still do training test split, right? So you train your classifier, like not classifier, the regression, and then you can evaluate this risk on the test part, right? So if I want to do the like evaluate, let's say Nadaria-Watson estimator, eta hat x, like summation k xi x. It's actually, it would be like the translation invariant one, like k xi minus x over h yi divided by k naught xi minus x divided by h. So if I want to do that, what I can do is like I have my own like test set, which I got by a splitting, right? You can still split. This is going to be like tilde I from 1 to m. And then I'm going to form, instead of like the indicator this is gonna be, can anyone tell me how to write the test there? Like risk test eta hat. What do I want here? These are my test data. How do I calculate the? It's actually like going to be the yeah, this is going to be a little bit tricky because it's actually not tricky. So how do I do it? So that's my risk. Just plug in everything, every time you want to estimate, it's like empirical estimate of the loss. So you'd have like y hat, which is going to be like your eta hat applied to xi tilde. That's this is a new data set that you haven't seen in training. You apply it, this is going to be your y, and then you measure the difference with the actual y. So it's going to be just 1 over m summation I from 1 to m, eta hat x tilde I minus y tilde I squared. So this comes from the training. You apply it to each one of your test data and compare with the corresponding y. You take the average. That would be your test MSE. Okay. So this empirical average is just replacing the expectation. So you want the expectation over a generic sample here. And this would be like f of, or like eta hat of x, but you don't have a generic sample, you average from where you're trying to approximate the actual risk. So this would be like test MSE, which is like an approximation of the true MSE, which is the risk in this case. Sounds good. Okay, that's how you do it in practice, but I want to do some calculations. So what I'm going to do is slightly different because I'm going to look at the risk instead of looking at it as a generic instead of looking at so these are all we know this is the decision rule, optimal decision rule. This turns out to be equal to eta, and we know how to estimate it, already have the estimators. Now I want to do some analysis, show you the bias variance trade-off. What I'm going to do is, what are we going to do? So this risk for a generic estimator is expectation of, again, f of x, this is y hat, minus y squared. You can write this as expectation of f of x minus y, conditional on x, that's inside, and then an expectation outside, so this squared. Has anyone seen something like this? So this is saying, for example, expectation, if I have like a random variable z, I can write the expectation as expectation of z conditional on x. So if you have two random variables, you condition z on y, take the expectation and take the expectation another time. It's called the Tower property or iterated expectation. Does that make sense? So this, you can think of it as just z. Right, so expectation of z, this is a random variable. Expectation of z given x. some z. Does it make sense? Or have you seen something like this? No. Now you've seen it. So this is a very important property of conditional expectation. So conditional, when you want to, like, you have the expectation of z given x, this would be a function of x. This is like the regression function for estimating z given x. And the expectation of that would be the expectation of z itself. Okay, so if you want to, like in the previous notation, remember eta of x was expectation of y given x is equal to x. So eta of like a random x from the distribution would be like just this. And if I take the expectation of eta of x, this is saying the expectation of the regression function at the generic x would be the same as the expectation of y given x. This turns out to be the expectation of y. So the expectation of your regression function of the generic x is the same as the expectation of y. This is a very well-known property of conditional expectation. So a smoothing property and like tower property, like law of iterated expectation, has many names. Okay. I'm going to assume that you know this from a previous course, which doesn't look like it, but Google this. It's a very important. Maybe we can talk about this later. It's not of super concern to us, but it's very good to remember this. Okay, that expectation, like if you take the expectation of conditional expectation, you get back the expectation of the original variable that you were trying to condition on something else. So I can always write this like that. And then you can like focus on, what I'm gonna do for simplicity, I'm gonna focus on this part. What I'm gonna do is basically, I'm gonna calculate this at a particular like little x minus y squared conditional on x is equal to x. So I'm gonna focus on calculating this because the other one is like the average of this over all x's. So you can think of this as this outer integral is averaging over x. This is saying for every particular x what happens. So what I'm going to do is focus on the value of the regression, of the valued estimate. So this is my regression estimate. I'm going to look at the particular value and see what it is. So the way that it works is like if you look at these, like these things that we had. So this is some sort of an average error across all the x's. What I'm going to do is like I'm going to focus on a single x here. See how this estimate varies here. Later on, you can vary x and you can try to take the average. But this is going to simplify my life. Okay, so we have like conditional on the test being like this x, this y will have some variation. I'm going to let that variation remain in the model. So there's some variance here. So if I observe this example, sometimes y is that, sometimes y is something else. So that variation is going to work with. Otherwise, I'm going to fix x here. Okay, so that's going to be the thing that I'm going to analyze. So from now on, actually, let's see what I did here. Yeah, okay, so it's going to be a little bit more tricky. Let's see. Any questions? Let's see how we can. Does that sort of make sense? So we're going to analyze this conditional risk. So if you expand this, what I'm going to do is I'm going to do f of x minus eta of x plus eta of x minus y squared. Okay, add and subtract the actual regression function. And then I'm going to expand. So what happens here is f of x minus yeah, okay, so what we get is something like this. Squared. If you expand and then let the conditioning, let me put the conditioning on top. So I'm going to use this notation for simplicity. So to simplify, so let's write, let us write. I'm going to write expectation x on top of whatever to mean expectation of that whatever condition on x being equal to x to simplify my writing. Okay, so this would be like expectation on x, and I'm going to expand. So I get f of x minus eta of x squared plus 2 f of x minus eta of x times eta x minus y plus eta x minus y squared. Okay. And then I separate everything. So I get expectation of x, f of x minus eta of x squared plus that thing, 2 f of x minus eta x minus y plus expectation of x eta x minus y squared. Okay, so I get 3 terms. What I did, I just subtracted, so I had subtracted this guy, which is really the conditional expectation of y given x, or in the notation that I'm using here, expectation x, y. Okay, that's our true regression function. Just expand it and then put the expectation there. Sounds good. Add and subtract this. Square the thing and then go that root. Sounds good so far. What I want to claim is that this thing is constant and comes out of expectation. Is that true? Because of the conditioning and conditioning on x being equal to x, so there's like fixed. So there's no x, you can see this x is fixed. So this comes out. There's no reason to carry the expectation there. There's nothing random. The randomness is only in y here. So this comes out. Right. And then I have, for the second term, again, this term is constant, comes out of the expectation. So I get 2 f of x minus eta of x times expectation of x, eta x minus y, and then the last term. Okay, so what is this? Let's see if anyone can tell me what this is. The expanded quadratic function. So this is, yeah, so this is really, if you expand the notation, this is saying expectation of eta x minus y conditional on x being equal to x, right? Because eta x is like fixed here. So eta x comes out, this is really minus expectation of y given x is equal to x, right? So I'm applying the expectation here to this. Things are linear, eta x is fixed. So this comes out, and I hear the 0. This is really equal to eta x, so this is actually 0. Oh, sorry. So this is really 0. Okay, so this term goes away actually. So this is 0. So this middle term goes away. So the end result is, if I write from the top, so you see like expectation of this conditional thing that I was looking at, minus y squared. This is my quadratic loss conditional on x. This is going to be the first term, which is f of x minus eta x squared. That's this term. And then the other term is the last one here, which is, I'm going to expand again. It's just going to be expectation of shorthand notation is going to be gone. This squared conditional on x is equal to x. Okay. Right, so this plus that, the middle term vanished, because if you think about this, that expectation of y conditional on x is just eta x. So, and I get that. Does that sound good? It was a little bit tricky, but not too much. Okay, we just added and subtracted, the cross term vanished. So go through this argument. It's not something that this is not the main thing that I want to argue, but it's good to do as an exercise. What ends up happening is, this is my conditional risk, right, that I was caring about. This is saying that if I want to compute this, basically I'm comparing the f, this is a candidate regression estimator, to the optimal one, the squared, and then there's this part. This is very similar to this, but with f replaced with eta. So this is like conditional risk of f. This is conditional risk of eta. And you can, from this equality, see that for every point x, because this term is positive, the conditional risk of any other estimator would be at least as much as this. So this is better, because the conditional risk of any other estimator other than eta, this term would be non-zero. For eta, this is going to be zero, they're the same. If f is different at eta at x, you're going to pay this penalty term. Right, so this sort of prove also that eta is optimal. What I'll say is that this conditional risk, there is this part which I can't improve. This is the unimprovable part of the risk. So like unimprovable. This is like the Bayes risk, if you remember. So if you have an additive regression model, this would be basically the variance of the noise in the model. There is a level of noise that I can, so the best estimator minus y squared, if you calculate this is related to the conditional variance. So this is the y, so this is y, this is the conditional expectation of y given x, so this is a conditional variance of, so equal to the variance of y conditional on x. You can argue this because this is expectation of y given x. So this is the conditional variance of y given x. This is not improvable. There is a certain level of noise for every x in the model. So unimprovable, like the bottom sort of, this is the best that we can do. The thing that I can improve is this part. So the closer I get to eta. So I can, instead of working with the conditional, so instead of working with the risk, we work with the conditional risk for simplicity. And instead of conditional risk, I can just look at the difference between the actual, like the estimator and the optimal function. So this is what I want to focus next. So the risk, so decomposes into two parts. One, which I can improve, and it's related with conditional variance of y given x. And there is a part that I can improve by just taking this to be equal to that. But basically what it's saying is that you just have to like worry about the difference between your eta hat. So for example, I want to, like for a given eta hat, we're going to worry, we are going to worry about eta hat x minus eta x. So that's the quantity that I'm going to try to control, which we could have started with. Like this is reasonable to do, but I just want to say that the risk sort of boils down to conditional risk that actually boils down to this. If you take expectation of both sides, basically over x, you can see that this would be also equal to the, if this was a random thing, we're basically calculating the difference on average of our estimators for. But let's not do that. I'm going to focus on this because I'm going to do it for f eta hat that we want instead of f. So the difference between eta hat and x is basically what controls the conditional risk. Okay. So this is saying if you want to predict like your y performance on y is going to be how close you are to the actual regression function versus how close the regression function is to y. This part I can't improve because there's the limit of the problem. This part I can improve. So I'm going to focus on that. Sounds good? Yes.
What's the words after the we are going to?
We're going to, actually, I don't know. We're going to probably look at this quantity. Okay, I'm going to look at this, but there's also some variation in this. The variation in this is from the training, because this is going to be a random variable. So that was for a fixed f. I sort of tried to argue for you that it's good to look at the difference with this, the regression function. This is the same. This controls the prediction performance. So the prediction performance, there is a level of noise in y that you can improve beyond eta. So I really see that. I mean, just compare the value of f to regression. How close you are to the regression function controls the MSE. And now I'm going to control, like, look at this one. This is our, like, this partitioning estimate given and such. But this is also variable. So there's a level of variation in this, which I have to deal with. So this would be a random variable. Although x is fixed, there's a variation here. So if you go at each one of these, what I'm going to do is, like, I'm going to look at a particular x here. And at that particular x, maybe this, let's say this black line is a true regression function. This is my estimator. And there is a variation across for that x as I vary my training sample. So I want to characterize that variation. That's what I actually want. That's where this variance is, like this sort of business of bias variance trade-off is coming from. So that's what I'm going to control. So what I'm going to do is, we don't have much time, but I'm going to introduce some notation. What I want to do is, like, look at the expectation of this. This is like in this next level of MSE, but for analysis, we're going to look at this expectation tilde, where this expectation tilde is going to be my notation for expectation conditional on the training data. So whatever I put inside, I want to compute the conditional expectation. So this is not going to be random. I just want to look at what is the average as I vary my training. So, like, sorry, that is a vary. So this is a little bit tricky. So as I vary y, so I'm going to condition on the x's in the training. That's what I'm going to do. The reason this will simplify. So what is varying here is the y's for x's. So once I condition on this, I'm going to assume that I observe these training data points, but I'm not going to assume the values of y. Every time I repeat the experiment, I keep the x's, but I let the model pick the y's. And I want to see how much I vary on average. So this is like an MSE between the actual function and this, because I condition on this now, this is actually this is not fixed. So there's randomness, and because of the y's, this is fixed. And so the only randomness here is randomness from yi's, like I from 1 to n from the training. So if you fix the x's, some y's are random. There's a noise in the model. I'm going to just capture that one. So I'm going to look at this. So all of this I did is that I want to analyze this. So we haven't started analysis yet. This is just to motivate what I'm going to look at. And this is the quantity that I'm going to look at. So the difference between the estimator and the true, like, optimal one, but conditional on fixing the x's in the training, letting y's vary. I want to see how much variation, how this is. Okay, so hopefully next time we're going to come back and analyze this and see the effect of the bandwidth. How does the bandwidth affect this? So this is another kind of MSE. This is, you can see it's like the mean, the squared error, but the error is between the regression of the actual function and this, and then the expectation is under some part of the training, not all of the training. Okay, this is the easiest one to analyze. That's why I picked this. But I sort of try to motivate this. This is related to the conditional risk and so on. Okay, questions? So I'm gonna post the slides, have a look at this, and hopefully there's also a discussion in the notes, the book that I uploaded. We're gonna go over the analysis and you're gonna see the bias variance trade-off. There's a bit of, I don't have it here, but there's a bit of interesting. So this would be probably the most technical thing that we're gonna do in this course, but it gives you a very nice intuition of what is this bias variance trade-off about, okay? And then we move on to something else. Okay, thank you guys. See you next time.